Hi, hello and welcome to BK'sTechStack. I am BK. Today we are going to learn about VectorStore, the embedding hub. In building sophisticated LLM applications, efficiently managing and retrieving data is paramount. VectorStores serve as the backbone for this, storing data in a format, embeddings, that allows your language model to quickly find and work with relevant information. This capability directly enhances the model's performance by providing rapid access to knowledge. Essentially, it's how your LLM keeps its vast knowledge organized and accessible.
When you're dealing with massive datasets and need lightning-fast similarity searches, FAISS is your go-to. Developed by Facebook AI, it's built for high performance and scales incredibly well. Teams leverage FAISS within LangChain for production environments where low-latency retrieval and handling large volumes of high-dimensional vector data are non-negotiable. This means your LLM can pull relevant information almost instantaneously, no matter the scale.
For those pushing LLM applications into enterprise-grade global deployments, Pinecone offers a compelling solution. As a fully managed cloud-native vector database, it takes care of the infrastructure, providing high availability and distributed search across geographies. Integrating with LangChain, Pinecone ensures your applications remain performant and scalable without the headache of managing the underlying vector storage. This allows you to focus purely on building your application, not the database. For developers in smaller projects, or when you're just kicking off an LLM application, ChromaDB is a fantastic choice. It's a lightweight, user-friendly vector store that handles local storage of embeddings with ease. Its simple setup and seamless integration with LangChain make it perfect for rapid prototyping and development environments, keeping cloud costs minimal. It lets you iterate quickly and efficiently without the complexity of a full-scale production system. Understanding how a vector store works is key to leveraging it. The process starts by taking your unstructured data, think text documents or images, and converting them into numerical embeddings. These vectors are then stored. When a user asks a question, that query is also converted into an embedding. The vector store then performs a similarity search, finding the most relevant stored embeddings to answer your query. This entire flow is critical for powering retrieval augmented generation, or RAG, applications.
While vector stores manage your embedded data, LangChain Retrievers are the dynamic explorers, reaching out to external sources to gather information crucial for your LLM. Unlike simple vector stores that just store and retrieve, retrievers are designed to take an unstructured query and intelligently fetch relevant documents. This versatility allows your LLM to pull in real-time or domain-specific knowledge, making its responses far more informed and accurate than it would be on its pre-trained data alone. Let's see a retriever in action. Imagine you have a large state-of-union.txt document. First, a text loader brings it in. Then, a character text splitter breaks it into manageable chunks. These chunks are embedded into vectors and stored in FAISS. When you ask, "What did the president say about Ketanji Brown Jackson?" the retriever takes your query, embeds it, searches FAISS for similar vectors, and returns the most relevant chunks. This is how your LLM gets precise contextual information from vast text sources. While a single LLM call is great for basic tasks, real-world applications often need a sequence of operations. That's where LangChain Chains come in. They allow you to link LLMs, prompts, and other components together, creating powerful multi-step workflows. Think of it like building a pipeline where the output of one step feeds directly into the next. Whether you use the traditional chain interface or the more flexible LCEL, understanding chains lets you construct highly sophisticated and structured LLM applications. The LLMChain is your foundational building block for structured interactions with an LLM. It essentially combines a template for your prompt with the language model itself. This allows you to dynamically insert specific inputs into your prompt before sending it to the LLM. For instance, you can ask, "What's an innovative name for a startup focusing on product?" The LLMChain fills in product and gets the answer, boosting the LLM's functionality for specific tasks. When your task requires more than just one LLM call, sequential chains are incredibly powerful. A simple sequential chain acts like a conductor, guiding a series of individual LLM chains where each step's output feeds directly into the next. Imagine you want to first come up with a catchy bookstore name and then immediately generate a unique tagline for it. By listing these two separate LLM chains, you can run this entire sequence with a single input, creating a coherent, multifaceted output. The stuff chain is one of the simplest ways to integrate documents into your LLM's context. It works by taking a list of documents and literally stuffing them all into a single prompt. This is particularly effective when you have just a few relatively short documents that can comfortably fit within your LLM's token limit. For instance, if you want your LLM to summarize a short meeting transcript, the stuff chain is a direct and efficient approach to pass that content.
When you're dealing with many documents and you need a nuanced, detailed answer that evolves with new information, the refined chain shines. Unlike stuffing everything at once, it processes documents one by one. The LLM gets an initial answer, then each subsequent document is used to refine or update that answer. This is like a meticulous editor, carefully integrating new details into an evolving narrative. It's perfect for detailed document analysis where context needs to be built progressively. For truly massive documents or many documents where a single prompt won't suffice, the map-reduce chain offers an elegant solution. It breaks down the problem, just like a team of artisans working on a large piece of art. The map step processes each part independently using an LLM. Then, the reduce step takes all those individual outputs and combines them into a single, coherent response. This approach effectively bypasses token limits, allowing your LLM to handle extensive data by processing it in chunks and then synthesizing the results. For any truly conversational LLM application, memory is non-negotiable. It allows your system to remember past interactions, preferences, or context, making conversations feel natural and continuous. Without memory, every LLM call would be like talking to someone who instantly forgets everything you just said. LangChain's memory system handles this by storing chat messages and other relevant data, ensuring your LLM can reference previous turns in a conversation and build coherent responses. LangChain offers several flavors of memory, each suited for different needs, but conversation buffer memory is a common starting point. This type keeps a buffer of the full raw chat history. When a user asks a question, this history is read, included in the prompt, and then the new question and the LLM's response are written back into the buffer. This ensures your LLM always has the immediate conversational context, leading to more relevant and engaging dialogue. It's like giving your LLM a short-term memory that expands with the conversation.
Sometimes an LLM alone isn't enough. It needs to interact with the outside world. That's where LangChain agents come in. Think of an agent as a smart assistant that can decide which tools to use, be it a search engine, a calculator, or a database, to accomplish a task. They effectively extend your LLM's capabilities far beyond its training data, allowing it to solve complex problems requiring external information or actions. This enables applications that are not just conversational, but genuinely functional and problem-solving. An agent's workflow is a continuous loop of decision-making and action. Given a task, the LLM-powered agent first decides which tool to use. Then it performs that action, such as searching Google or querying a database. It then observes the result of that action, evaluating if it's closer to solving the problem. This decide, perform, observe loop repeats until the agent successfully completes the task. This iterative process allows agents to tackle complex, multi-step problems dynamically.
Let's put an agent together. First, you'll need an LLM. Then you load the specific tools it needs, like the archive tool for research papers. Finally, you initialize the agent, connecting the LLM and its tools. When you then ask a question like, "Tell me about paper 2303.15056, the agent dynamically decides to use the archive tool, retrieves the paper's details, and synthesizes an answer for you. This exemplifies how agents can intelligently leverage external resources to provide highly specific and current information. Beneath many of LangChain's memory modules lies the Chat Message History class. This class acts as a dedicated organizer for your conversation logs, storing distinct human and AI messages. It's particularly useful when you need direct, programmatic control over the conversation history, perhaps to manipulate the messages before passing them to an LLM, or to simply inspect the flow of dialogue. It ensures you have a clear, structured record of every turn in your chat. Congratulations! You just learned presentation topic. Now it's your turn to apply these skills. Drop a comment below and let me know what you're building. If this helped, smash that like button, subscribe to BK'sTechStack for more weekly tutorials, and share this with someone who needs it. Visit www.BK'sTechStack.com for free resources, exclusive tips, and our community. Next video, we're diving deeper. Don't miss it.